Now we will go for recording purpose.
Good evening, sir.
Good evening. Good evening to
Yes, sir. Good
everyone.
evening.
Good evening to everyone. Just a moment. Let me go for recording the meeting. Okay. So we see that in our last two videos, we have been talking about the kinetics of rigid bodies, in the sense that we have talked about the kinetics of what is called as the pure translational motion, and then we talked about kinetics of pure rotational motion. So these two videos I shared with you. I could not take the live class because of your exam and all. So and today we will talk about the last type of kinetics, that is what is termed as the general plane motion of a rigid body. As you know from your knowledge of kinetics, that kinematics, sorry, when you have the general plane motion, or sometimes you can call it as GPM, the general plane motion. When you have the general plane motion, now when we see that there will be no point of the rigid body will be considered as a fixed, inertially fixed, number one. That means every point of the rigid body is in motion. That is number one. And number two is that during the course of the motion, the body changes its orientation. So it does not maintain its orientation. So this too means that the body is undergoing a combination of translational motion as well as the rotational motion with respect to a specific point. And in general, that specific point we normally considered as the center of mass of the rigid body. So therefore, for us, the in the class of kinetics, we can say that any general plane motion or GPM of a rigid body will be considered as a combination of translation and pure rotation about its center of mass. So these two taken together, we will form a general plane motion of the body. That is number one. Second assumption regarding this general plane motion is that the body we will consider here, that means this rigid body which we are going to consider here, this rigid body which we are going to consider here is a slab-like body. It's a slab-like body. Slab-like body means what? It means that the thickness of the body in the perpendicular direction to the plane of this board or plane of your khata or plane of your book is very, very small. So that is what is called as a slab-like. You may call this as a plate-like body also, plate. So it actually looks like a plate. Why we make these assumptions? Because we have certain things called mass moment of inertia of the body. This mass moment of inertia is a very tricky business about which you will be coming to know in your next semester when you will study the advanced dynamics or dynamics of rigid body, three-dimensional dynamics of rigid bodies. There you will come to understand the full the nature of this mass moment of inertia. But in our case, we are dealing with a very simplified case, and in our case the body will be, that means this rigid body which is undergoing a general plane motion GPM will be considered as a slab-like or a plate-like body, for which I told you that the thickness in the perpendicular direction to the plane of this motion is very, very small. So under such circumstances, we see from here that if we make these kind of assumptions here, we see, suppose that this is a a rigid body here, and this rigid body is subjected to different forces. Say, let us consider that it has force, say F1, let us name them. We call this force as F1, F2, right, dot dot dot. There are, say, n number of forces may be acting on the body. There may be various couples also. We can call this couple as, let us call this as, define it as, say, M1, and there can be other couples also. I just show only one for representation. And this body is having an angular acceleration, and the center of mass of this body is having a translational motion also. So let us represent the translational motion of the center of mass. Let us call this vector. Let us call this vector as the acceleration of the center of mass. Let us call it as A bar bar. So A bar represents acceleration of the center of mass, and this bar sign we can call the vector which represents this. So in that way, actually these are also, these are also what should I say, are the vector quantities. So we must actually assign these arrows on top of them to indicate that this is a vector quantity. Though in two-dimensional motion, actually it is not necessary that you have to apply the vector concept. You can use the scalar concepts also. For this purpose, let us consider that we have some reference frame. That reference frame is X and Y. This reference frame is not inertial reference frame. This is the reference frame which is rigidly locked to this body at the center of mass, which is shown here. You see, this origin is here, the thing called C. C is the center of mass of the body. So I have this reference frame which is rigidly locked to the body at the center of mass, and there is another reference frame which is capital X, capital Y. Let us assume that they share identical directions at this instant, because this will be always, always in this direction and in this direction, because it is called inertial reference frame. This is termed as the inertial frame, and this one is not inertial frame. This one is actually body fitted frame. That means what we do, we fit this reference frame on this body at the center of mass and allow this reference frame to rotate with the body with respect to this reference frame. So essentially this x-axis and y-axis will not at every time will be aligned along capital X and capital Y directions, but instantaneously. So this is an instantaneous representation, you must remember, instantaneous representation. So this instantaneous representation is there. This instantaneous representation is there. So it is instantaneous. At this instant, you have this body in this direction, acceleration of the center of mass is in this direction, the forces are aligned along this direction, etc., etc. So as we know that the action of these forces and the moments which may be there acting on this rigid body is basically equivalent to the acceleration. You see, this is the acceleration of the mass center, so it must be equal to the sum of all the forces by Newton's second law, generalized second law. From our knowledge of system of mass particles, we know that the vector sum of all these external forces must be equal to m a bar bar. So this a bar, that means the acceleration of the center of mass, I should say instantaneous acceleration of the center of mass, is resolved into two components, one along this x-axis, one along this y-axis. So I call it as m a bar x and m a bar y. These are the components of this vector, pink vector. And we know that from our rotation business, we know that the moment of all these forces with respect to the center of mass is generally equal to I bar into alpha. Why it is so? We have explained it in our previous class video where we discussed the pure rotation of a rigid body. So it should be equal to I bar alpha, where I bar is termed as the mass moment of inertia of this body about an axis perpendicular to the plane of this body, perpendicular to the plane of this body. That means if this is x-axis, this is y-axis, then perpendicular will be z-axis. So this I bar is about the z-axis. Okay, I bar is about the z-axis, and this is the mass moment of inertia of this entire body about the z-axis, which is passing through the center of mass, and that multiplied by the angular acceleration of this rigid body, instantaneous angular acceleration. So that is the resultant couple I bar alpha. So in the nutshell, we can therefore see that these are our relevant equations of motion. These are termed as the equations of motion. That means they govern the entire kinetics. What it says, the first one, this is the force equation, which is coming from the generalized Newton's second law. This is the vector equation, which is scalarly written into the two components, one along the x-axis, other along the y-axis. So I write summation fx equal to m a bar x, summation fy equal to m a bar y, and this summation fx indicate the algebraic sum of all these external forces along this x-axis. Similarly, summation fy will indicate the algebraic sum of the components of all these external forces along the y-axis. Correct? So these are all, you should always remember, keep it in mind that they are all instantaneous representations. So you see, these are your equations. And finally, if we take, because all these forces are distributed at the different locations on the body, these are points of applications of the forces are at various locations on the body. So therefore, it is legitimate that we can consider the moment of such forces about some point, and in this case, that point is the center of mass. So always you need to write this moment equation with respect to the center of mass, because if you recall, this equation comes from the equation which we discussed in connection with the system of mass particles, that sigma m bar a is equal to h bar a rel dot. You remember this equation we have, h bar a rel dot. This equation we discussed in connection with our system of mass particles, and we said that this equation is applicable when A is either inertially fixed, when A is the COM, center of mass of the body, and there is a third option which is rather a very peculiar option, which states that the point A should be a point whose acceleration is directed towards its position vector, relative position vector of the center of mass with respect to this point. So these are the three conditions under which we can write this equation, if you recall your system of mass particle study. So from this equation we extended, and I showed it in connection with the pure rotation, that this equation can ultimately be simplified to this form. But if you just compare with the third equation with the equation that we used in pure rotation, we had an option there. We could use this with respect to the center of mass as we have done here. Also, we could have used that equation with respect to the fixed center of rotation, which need not be the center of mass, because I told you that the pure rotation can be non-centroidal. That means the center of rotation of the body may not be the center of mass of the body, that is non-centroidal rotation, or it may be centroidal rotation, in which case the body will purely rotate about its center of mass. Correct? So your center of rotation may not be equal to the center of mass. So when the center of rotation is not equal to the center of mass, in that case you have two options. Either you can use the point O. O is termed as the this O represents the center of rotation of the body, or you can use the center of mass of the body. So this you have an option in writing this equation, but unfortunately in case of general plane motion we don't have this option for using O. So what we have to do is we have to write this moment equation with respect to the center of mass only. So therefore my third equation, that means the moment equation for this case, will be this. Very plainly you can think, someone can say wonder why there will be moment equation. So very simplistically put, why there will be moment equation? Very simplistically put, you can argue it in that way. You can convince your other friend who is not actually very much clear that why we should be having a force and why we should be having moment equation simultaneously in describing its equation of motion. To convince him, you can just plainly, without going much into the deep inside the dynamics, you can convince him or her like that. Say in this case your body is having a combination kinematics. It is having translational motion, it is having rotational motion. So very vaguely you can tell that there should be an equation which takes care of, correct, the translational motion of the body, and there should be an equation which should take care of the rotational motion of the body. So the translational motion will be taken care of by this force equation, and the rotational motion will be taken care of by the moment equation. So here summation MC represents what? It represents the moment of all these external forces as well as some external couples. There may be external couples as also. So sum of the moments of all these external forces about the center of mass, to it you add any external couple which is acting on the body, because for a rigid body couple is a free vector. So instead of say the couple is acting say somewhere at this point, so you can consider that the couple is as good as it is acting at the center of mass as well. So therefore you can shift it from its current location to there, because couple is a free vector in case of a rigid body. In case of deformable body it is not so, because deformable body all vectors will be locked vectors. They should be locked at their current positions. But in case of this is actually it's a free vector. So therefore you see summation MC not only takes care of the moment of all these forces with respect to the center of mass, it takes care of the sum of all the external couples which is acting on the body, and that should be equal to I bar into alpha, because you are writing it with respect to center of mass. So this I, that means the mass moment of inertia, should be calculated with respect to an axis which is perpendicular to the plane of motion and passing through the center of mass. So that is therefore the implication of these three equations. So I have therefore three equations, independent equations at my disposal, the 2 force and 1 moment equation. So I can therefore solve maximum 3 number of unknowns in this problem. So you should be pretty clear that if there are more than in case of 3 number, in case of when the unknown quantity becomes more, then you have to have some additional equation which will take care of that extra unknown. However, if such GPM, that means the general plane motion, is constrained, What is meant by constrained motion? Such as rolling of a disc without slipping. Say we have a rolling motion problem in which a disc is just rolling on a flat surface or on a curved surface without slipping. There we have a kinematic constraint relation, and that kinematic constraint relation can be used to set up the relations between this a bar x, a bar y and alpha. We will explain this particular comment, this observation, right? And how we will be doing it, we can take it with an example. So if we now move on to our, this example. So let's consider this, this is actually basic theory is this. So that is pretty, concise and precise. See here, you have two force equations and one moment equation, and that also needs to be written with respect to the center of mass. However, you see that certain exceptions can be taken care, can be made when your motion is a constrained motion, such as a rolling motion problem. So in GPM, the rolling motion problem plays a very vital role. So let's actually take care of that rolling motion, explain that rolling motion problem from the book of Merriam and Craig with this example. Actually, this is problem number 6/89 we will be dealing with, but since this 6/89 problem is actually taking all the data from the problem 6/88, so actually our problem is the problem that we are going to solve here. The problem that we are going to solve here is 6/89, correct? So this is the problem that we are going to solve. But that 6/89 is actually taking the data from 6/88. So I just take here the circular disc of 200 millimeter radius. So this is the circular disc of 200 millimeter radius, has a mass which is 25 kg. This disc is having a mass of 25 kg with centroidal radius of gyration k bar. You see, this is centroidal radius of gyration. Please note this term, centroidal radius of gyration. You remember we have this I bar. This I bar is actually equal to integration over the entire mass domain r squared dm. And this integration can also be written as this is mk bar square. So this k bar is therefore termed as the radius, centroidal radius of gyration. So the centroidal radius of gyration, that means this is G represents centroid. So you consider, imagine that there is an axis which is passing through the G and perpendicular to the plane of this screen, that means coming out towards you, that axis. Above that axis, that I bar is there and its centroidal radius of gyration is 175 millimeter and has a concentric circular groove. So there is a concentric circular groove here, and that groove is of radius 75 millimeter. That means if we take the side view, if we take the side view of this figure, then it will be clear to you. The side view of this will look like this. This is the basic, this disc. This is the surface, and here you have that small hub, right? That small hub takes care of that. So the radius of this hub is 75 millimeter. And there is a cord wrapped around this hub. You may have seen this type of devices when you see the cable lines are laid down by the wooden rollers. Have you seen such kind of things? The roller is the telephone cable lines, then the nowadays the optical cable lines, right? They are actually being laid down by rolling these big wooden rollers. So you see these wires are actually wound around this. Actually, there is a symmetric thing. That means there is another, the roller here kind of thing is there. Double roller kind of thing is there. Then this hub connects both of them. And this wire is wound around this hub. And what is done is that this roller is being rolled on the surface, and the cables are unwound from this, and these are being used to lay under the ground or under the road surface for communication purpose and all. So we have this kind of business here. A steady force T is applied at an angle theta. So this is the angle at an angle theta. You see the steady force T is being applied to a cord which is wrapped around the groove as shown. So this is the figure. Now here the thing I have blackened out is actually the data for problem number 6 by 88. So in order to avoid any sort of confusion, I have blackened it out from the thing. You can get the thing, of course, from the 7th edition PDF copy, what is written over there. So you see that here the data is that this T, that means this force is to be taken to be equal to 50 Newton. This is the value, T to be taken equal to 50 Newton. And the value of theta is taken to be equal to 30 degree, because these are actually the data for problem number 6 by 89, which we are going to solve now. It is given that the coefficient of static friction and the coefficient of kinetic friction between this roller surface and the road surface are respectively 0.1 and 0.08. What we need to find out is, that's a common thing between 688 and 689. You need to determine the angular acceleration of the disc because of this action of this force, and the acceleration of the center of mass of the disc, and the friction force here which acts, which the surface exerts on the disc. So there are so many things that you need to find out: acceleration, angular acceleration, linear acceleration of the center of mass, and the friction force that exists between this disc and the surface. So this is normally a typical rolling motion problem. So when these data are being given, that means both this static coefficient and kinetic coefficient data are being given to us, we need to ascertain whether this rolling is a perfect rolling or it is not a perfect rolling condition. So to begin with our problem, it is always customary to assume that we have a perfect rolling motion problem in this case. So if we have a perfect rolling motion problem here, so that means perfect rolling motion condition prevails. It means that the friction that is available here between the guide, between the roller and the surface, the friction that is available here between the roller and the surface is actually, is sufficient to make this point, I mean to say this point of contact, as to be the point of no slip point. So this point, if of course we assume this to be a perfect rolling problem, if it is not perfect rolling, then it means that this point will be no slip, it will never be no slip point. That means there will be a slip between these two. So actually, it is no slip means what? It means the kinematic condition of this surface and the kinematic condition of this surface must be identical. So what is the kinematic condition of this surface? Now it is static. It is not moving. So essentially, this means that this particular point at this instant, because this point will change after delta t time, some other point will come and make a contact with this road surface. So therefore, this is an instantaneous point of contact, and we assume that this instantaneous point of contact is actually, it's a no slip, so it means that its velocity is zero. So it is called as the instantaneous center of rotation of this body. So we see that if we assume all these things for a perfect rolling motion, then it is noted that with respect to this point, because of this tension, we see that this is trying to rotate the wheel in the clockwise direction. So Having ascertained that this wheel will be having a tendency to rotate in the clockwise direction, I can now draw the free body diagram of this disc. You see, the free body diagram will consist of the force 25 G Newton, that's the weight. There will be this T external force is there, and we will be having some normal reaction, and let us assume that this is the direction of the friction force. So you have, therefore you see that this is FF, the friction force. I just arbitrarily, as I need sense that it is acting towards left, and under the action of all these forces and all, you see this point is trying to maintain a no slip motion. I mean to say it is ideally rolling. So ideal rolling we have already discussed in our absolute motion analysis class. In ideal rolling, we see that that if this one tries to roll in this direction, then the acceleration of the center of mass will be towards along this, right? So therefore you have the acceleration of the center of mass will be along the x-axis, and I have, this is 25 A bar is the total force that will be generating, and because it is rotating, we have this I bar alpha, and all are with respect to the center of mass. So our equations of motions will be what? Simply, we will be writing, because you see the acceleration of the center of mass along it is only along this x direction. It does not have acceleration along the y direction. So it means that along the y direction, static equilibrium condition prevails. So I can have along the x direction equation, I can write that this equation is t cos theta. This is the cos component minus ff, because we have arbitrarily assumed that ff is acting in this direction. T cos theta minus ff is equal to m a bar x. And if I substitute the t values and all, we see that because we have assumed the perfect rolling motion, of course we have this relationship that is existing, that is a bar. That means if this is a bar, right, if this is a bar and if this is alpha, and if this radius is r, then definitely we can write that a bar is equal to r into alpha. We know it from our kinematic analysis. In this case, this radius is full r1 radius. I have assumed this greater radius as r1 and smaller radius as r2. So naturally I can write a bar equal to r1 into alpha. So if I write our equation along the x-axis, equation of motion, then this will be our equation, and in place of a bar I can put this and write, I can use this equation 1 and can convert it in terms of alpha. Please note, we are assuming it perfect rolling condition, and that's why we are writing this equation. Okay, good. And in this in the y direction, as you know that there is no acceleration in the y direction, so I must be having this side equal to 0, and I substitute all the numericals here, and it is known that Na, that means this normal reaction, is found to be something like this, 220.25 Newton on substituting your numerical values. So I have exhausted my two force equations, of course. Now I am going to write the moment equation with respect to the center of mass. So what we will do? We will take care of the moment of all these forces as disclosed in the free body diagram with respect to the center of mass. So naturally what I do, I just drop a perpendicular here to calculate the moment of this 50 Newton, and I can therefore say that this this will be definitely the radius, smaller radius, because this is tangential to the smaller circle. So the perpendicular is of course the the radius of the smaller circle. So I have therefore we take here clockwise moment as positive. I just symbolically show it by putting a clockwise arrow with a plus sign. This indicates that the clockwise moment is taken as positive. This is just an arbitrary case. One can take anti-clockwise movement positive as well. So here I have taken the clockwise movement positive and can write therefore that the moment created by the frictional force, that will be clockwise with respect to the center of mass. So that will be Ff multiplied by this entire radius, that is 0.2, minus the moment created by this 50 Newton with respect to the center of mass. Why it is minus? Because it is producing anti-clockwise moment with respect to the center of mass. So I have, this is 50 into 0.075, that is minus, and that should be equal to I bar into alpha. And you remember what is I bar? I bar can be written as m into k bar square into alpha, because here the centroidal radius of gyration has been given. And please note that the sense of rotation of this wheel, because if it is, you are assuming this to be a perfect rolling motion, then always you need to consider this as to be your center of rotation instantaneous. So you need to take care of the fact how this force is trying to rotate with respect to this point. Because you see, with respect to the center of mass, this torque force is having a tendency to rotate it in the anti-clockwise sense. However, with respect to the center of mass, it is trying to rotate it with respect to the clockwise sense. So you need to decide between the two that which one will be actually your sense of rotation. Physically thinking, of course, you can see that this is going to be your going to be the sense of rotation will be the clockwise only, because you need to take care of the rotating tendency of this force with respect to the instantaneous center of rotation, not with respect to the center of mass. So this will be actually the sense of the sense of rotational motion of this wheel. So I therefore take this equation, put it here, and from here definitely I have a relationship between F and alpha. So this is the relation that I get. So I get an equation 4, and also I have equation 2. So I can use these two equations. So just let me tell you here before we actually make an attempt, what are the unknowns here? Of course, what are the unknowns here? Let us see. The unknowns here, if we go on listing the things, the unknowns are acceleration of the center of mass, angular acceleration of the disc, the friction force, and the normal reaction, that is capital NA. So this 1, 2, 3, 4. Four unknowns are there, but we just now said that we have 3 equations at our disposal. So how we are going to solve the fourth unknown? The fourth unknown we are going to solve is that together with these 3 equations, I have one more additional equation which is coming coming from this kinematic constraint. So that's the thing that I actually tried to make the comment in my previous page. So if you go to my previous page where I made a comment here, I said that in cases the GPM is constrained, we have to use a kinematic relationship between the components of acceleration and the angular acceleration. Here, of course, we are fortunate in the sense that we don't have the 2 components of acceleration, but of course the component of acceleration that we have, that we can maintain, and we can use a kinematic relationship between them. So therefore altogether I have 4 number of equations. This is 1, this is 2, this is 3, and this is 4. So the 3 force moment equations and 1 kinematic relation, this 3 plus 1 make 4, and that will create my life comfortable, and I can comfortably solve for my unknowns. So actually, if I solve these unknowns, I use this equation 2 and 4 simultaneously and solve the figures, I get that this is the value of alpha, which turns out to be positive. So I see therefore my sense is correct, and my friction force, it is also turning to be positive. So it means that really speaking, the friction force is truly acting towards left, because I said in the beginning, I do not know in which direction the friction force will be acting. So I use this sense quite arbitrarily to actually proceed with our analysis. However, we are lucky that we turn out to be correct, and you see the friction force becomes like this. If you are unlucky, what you will get a minus sign. However, your magnitude will remain the same provided you do not make any numerical mistake, and as a result you can rectify that friction force sense. That means it is not towards right, it will be towards left. However, once we get, but you see the entire analysis thus far, the entire analysis that we have done is actually, relying on our assumption. And what was our assumption? That we are assuming it to be a perfect rolling motion. But really, is it a perfect rolling motion or not? That we need to now justify. And how we can justify that? Now you need to see that the friction force, that is you calculate from here, right? That has to be less or equal to the maximum friction force that is available at this point. So it means that if your surface is little bit slippery, that means you put some oil or you put some water on this surface, that will obviously reduce the attrition between the two and will try to reduce this value of mu s. So if this mu s becomes less amount of friction force will be available here, and that may not be sufficient to warrant the condition that you will be having, or rather to guarantee the condition that you will be having a perfect rolling motion here. So therefore, it will be our duty to check whether really the perfect rolling motion is prevailing here or not. So how that we can do? Now we can calculate, we have already calculated the friction force, and now I compare it with our maximum value of the friction force. Either that way you can compare, or the way I have compared it is something like this. I have calculated based on this value of the friction force, I have calculated how much is the static coefficient of friction we are having. And we see that it turns out to be 0.197, which is much greater than the available maximum static coefficient of friction. Either this way you can compare, or you could have done it like that. You could have calculated the maximum friction force, FF max. The maximum friction force available will be mu s, that means 0.1 into the friction force value, that means 43.301 Newton. So 43.30 Newton. So 0.1 means how much it will be? It will be 4.3301 Newton. So small a value. I'm sorry, I made a mistake. Sorry, it is not 43.301. Sorry, the normal reaction that I have to take. So it is 0.1, and the normal reaction value where I have got, I get it here, 220.25 Newton. Sorry. So it needs to be multiplied by 220.25 Newton. So therefore, we see that when we multiply it by 0.1, I find that this becomes equal to 22.025 Newton. So that is the maximum possible friction force here. But my requirement is much higher. It is 43.301 Newton. So obviously, the friction is not able to supply this amount of friction force. So obviously, we can therefore say that here perfect rolling is not possible. So our assumption is wrong. So we see that it is a case of rolling with slipping. So it means that your A bar is not equal to R1 into alpha, which we started assumed initially and did the calculation. So one thing pretty sure now, since there is a slipping thing, so I know now the friction force. How much is the friction force? It is not 43.301 Newton. Now it will be given by that it is mu k into Na. That means now you have to use the coefficient of kinetic friction in order to do that. So since your coefficient of kinetic friction is 0.08, you can see therefore your actual friction force value is 17.62 Newton, much less than the friction that I require to ensure perfect rolling motion. So actual friction force that we are having now is 17.62 Newton. So what we have to do? Again, we have to go back to our previous equations without assuming any relationship between A bar and alpha. So I have to now find out A bar and alpha separately. So A bar can be calculated from the second equation. So this is from where I can calculate your A bar, which turns out to be 1.0272 meter per second square, and alpha I can get it from the moment equation, that means the fourth equation, and you see this A bar is turning out to be positive. So it is very interesting to note that if this is the disk, A bar is turning out to be as expected. However, the alpha is not along this direction, rather your alpha is along this direction. So that is a very peculiar thing we are getting. So it means that because why it is so, why they are in this order, it is because that this wheel is not actually following rolling without slipping condition. It actually rolls with slipping. So in fact we can actually check exactly there is a slipping. How we can do that? We can do it in this way. So this is just a small kinematic check. We try to find out what is the velocity of the point A, which is the point of contact. Correct? The point A is the point of contact, and we write the velocity equation with respect to the center of mass, and we assume that we are taking over the time interval delta t, for which this A bar and alpha are constant. So if therefore we substitute all these values, we see that the velocity of point A turns out to be greater than it is. If you actually calculate, this is going to be greater than 0. But really speaking, I should have expected, because this point actually you see that this point is actually in contact with a fixed surface. So I expected that this point should have 0 velocity. Instead, what I find that this point is having a velocity like this. So it means that this is the surface, and on the top of this there is a point. You expected that there should be there should not be no relative motion between the two. In reality, there is a relative motion between them. So this actually tries to move in this direction, and that's why your friction force is coming in the opposite direction, because you have a tendency of having a movement along the positive x direction. So your friction force must be in the negative x-axis direction. So you see, everything falls in the pieces, in the boxes. Everything fits into the correct boxes. And all our calculations can be, logically can be explained to someone that, see, all our analysis are basically, results are basically consistent in nature. There is no inherent consistency in our calculation. So therefore, we can see that finally, I report that our answers are something like this. We have our friction force given by this. We have our acceleration given by this, and we have our angular acceleration given by this. Please note, when reporting, you need to specify their senses. Without sense, If the question is find the angular acceleration, and angular acceleration, you just report this answer, then you are 50% correct. Correct. Why you are 50%? Why not you are 100% correct? Because angular acceleration is a vector quantity, and since it's a vector quantity, you have to find out that vector. So not only you have to specify its magnitude, you need to specify its sense and direction as well. So you see that you need to specify in this manner. So please be very careful when you will be answering this type of question, that you find omuk velocity, omuk acceleration, something like that. Please keep it in mind. Not only you have to specify your magnitude, you need to specify their directions also. So I hope that this example is pretty clear to you. If you have any question, feel free to unmute yourself and ask me. But this rolling motion problem is a very important problem as far as the GPM is concerned. So if you do not have any specific query onto this example, then we can of course move on to our next part. So let's go and take up the second example. So this is the second example taken from the book of Merriam and Craig, and this is a 6/100 problem wherein we have a T-shaped body. Say this is a T-shaped body. You see, I told you that the body should be plate-like. Your earlier disc problem also the disc was plate, and here also this is a plate because the thickness in the perpendicular directions are very small. The T-shaped body of mass m is composed of two identical slender bars welded together as shown. Now this is a very thing that keeping this head of the T vertical and the leg of the T perfectly horizontal, the one end of the leg is attached to a roller and which actually is constrained to move along an inclined guide. Correct. Now if the body is at this condition is released from the rest, obviously this will try to fall. Correct. So it means that, and this one will try to move, so it means that this body will be under GPM. Correct. So if the body is released from the rest in the vertical position in the position shown, that means this is the instantaneous position. Find the initial acceleration of the point A. Neglect the mass and friction of the roller. So that's the thing. Very good. So this is in vertical plane. I show it here. I just draw the free body diagram. So this is the free body diagram. There is a normal reaction here offered by the guide. I assume this is the sense arbitrarily because it is both way guided. So the normal reaction can be this way or it can be that way. I do not know. I put an arbitrary sense. And I have the self weight of the entire system. And its center of mass is of course at a distance of L/4 from this head. How you can calculate it? Just by applying this principle of composite bodies, we can calculate that where its this combined shape, where will be its center of mass. Correct. So I just apply that equation m1 x1 bar plus m2 x2 bar dot divided by m1 plus m2 plus dot. That will give me the overall coordinate of the center of mass of the body. So if we follow that, I find that this distance is L/4 where actually your center of mass is. So I just resolve the self weight of the, because I take this as the x-axis, right? That means along the slot, I take this is as to be the x-axis, and perpendicular to it, I take it as the y-axis. And I resolve this self weight into these two components, one along this x direction, another along the y direction. So now let me assess. This is the free body diagram and this is the equivalent kinetic diagram. You have m a bar x, you have m a bar y. Of course, you don't have any a bar y because I'm sorry. You have g. Yes, g can have a bar x and a bar y both. So I have m a bar x and m a bar y, and we have this is I bar alpha. Okay. So how many unknowns are here? See, there are 4 unknowns. Again, we have 4 unknowns. So it means not only we have to use our dynamics equations, but also we have to use the kinematics equation. So let's see what about the kinematics. I quickly go through the kinetics part because now it is very simple to you that summation fx equal to m a bar x, from where you are directly getting the a bar x value, which turns out to be g cos 60 degree, means g by 2 or 0.5 g. So directly you get summation fy equal to m a bar y, because your the g is actually moving in a very queer path, so you do not know what is the locus of the g. So your acceleration will be having both directions, it will have. So you see your a bar y, you are not able to get it. So I just have na and a bar y coupled with each other by this equation. Forget it. And now I take the moment of all the forces with respect to the center of mass. So just use this, and you have the third equation, which is something like this. If you do the algebra, the equation turns out to be something like this. That means alpha equal to this and this and this. Okay. Beyond that, I do not know anything. So kinetics equations actually give me only these 3 results. One is this, one is this, another is this one. Fine. So now I have to try my luck with using the kinematic equation. Why we are using kinematic equation? Because I know that now I actually take the consideration something like this, because I have taken the acceleration of the center of mass, correct? The acceleration of the center of mass, so I write it like that. I take it here. Suppose I show it here. Suppose you see here that your acceleration of this is where your center of mass is, and your acceleration vector for the center of mass we have assumed arbitrarily to be like this. And now I know that this point's acceleration is of course known to me, that either it will be down the plane or it will be up the plane. So I use this fundamental relationship and thereby write the kinematic relations between the g and between the point A, right? So I write the acceleration equation between the point A and G in the vector format. Now, since you know that it is released from the condition of rest. So when it is released from the condition of rest, you see the omega, the initial angular velocity, right? That should be equal to 0, because it is initially allowed from the condition of rest. So I have therefore this vector equation. I can leave the third term and I am left with this one. So now I employ the vectors I and j and just apply the equation here and separate the I and j component. So you have this is I and this is j. Please remember that your A is having only the acceleration along the x-axis. You remember your x-axis is where? Your x-axis is of course along this slot. So since the point A is constrained to move along this slot, so it is therefore simple to understand that your acceleration of point A is along the I cap direction. It can be minus I cap as well. Your magnitude will turn out to be so. But it is at least noted that the acceleration will be along the x-axis. Either it will be positive or it will be negative. So since here I have both I and j, so essentially it means that the j component must be 0, because your acceleration is only having I component now. So j component is 0. So we have, this is our a bar y is this much. Now we find our, because you see, I can now use this equation to compute alpha, because I know what is my a bar y. You see, alpha is related with a bar y, and I have a relationship between a bar y and alpha. So I can use these two equations to solve for alpha. Correct? How to do that? For that you need to know how much your I bar, that means how much should be your mass moment of inertia of this combined body about the perpendicular axis through this point. So that we need to find out. Now here we will be having a good use of our parallel axis theorem. So this parallel axis theorem we have used here. We know a rod, the centroidal mass moment of inertia is 1 by 12 ml square. Now here we have to use m by 2 because your mass, total mass is actually divided into the two equal rods. So the vertical rod is having the mass m by 2 and the horizontal rod is also having the mass m by 2. So what we have done, simple. What we have done here, first we calculate I of this vertical rod, about this perpendicular axis. How much is that? That should be equal to, this should be equal to 1 by 12 m by 2 and L square. Correct? And now I have to take this axis from this position to this position. How much is the distance between these two? That is L by 4. Correct? This is L by 4. This is L by 4. So I apply the parallel axis theorem, shift this centroidal axis to this axis. And I have therefore the first equation, the first part of our I bar, that means this part, I use the separate color. This part, it takes care of the vertical rod, right? Now the horizontal rod. Now come to the horizontal rod. So this is the horizontal rod, okay? And where is its mass center? Its mass center will be at the middle point. So this is L by 2, correct? This much distance is L by 2. And you need to shift it from here to here. That means you need to shift it to L by 2 minus L by 4. How much? That is L by 4. So you need to shift your axis from here to here. That is also L by 4. So essentially the second one, you know, the second calculation, the second part, that means this part is for the horizontal rod and this part is for the vertical rod, and both should be same. Both should be same, and therefore you see that, you know, we add this together and we get, this is the thing. Now I'm sorry, both should not be same. Sorry, this is not technically correct. This is L by 2. Oh, I'm sorry. This is L by 2 minus L by 4. Na? So this is L by 2 minus L by 4. That means, okay, this is L by 4. So that is L by, sorry, that is L by 4. Very sorry. This is a board work plus time we are doing. So this is L by 4. L by 2 minus L by 4, and if you do the calculation, it turns out to be as something like this: 7 L square by 48. So that is your I bar about that. So now you put this I bar into our equation, into this equation I bar together with this value. So in place of a bar y, I put this value, and in place of I bar we put this value. So it's a difficult sum. You see, this sum is little bit difficult. So if you substitute it here and you make the arithmetic, you see your alpha turns out to be as 109 108 by 109 G by L, so much radian per second square. You should write the unit as well. Correct? And my objective is to find out acceleration of A. Correct? So how we can do that? You see, your acceleration of A is basically equal to this part. If you compare these two sides of the equation, you can see from here that acceleration of A is basically equal to a bar x minus 3 alpha L by 4 sine 30 degree. So actually a bar x is already known. A bar x is already known here. So you remember this is a bar x, that is already known. Only thing we are waiting for is to get the value of alpha. But alpha we could not get without NA. So I had to come through the complete course. And you see here, after getting this value of alpha, I put it into this equation only to find that the acceleration turns out to be positive, which means that our initial assumption is correct, that the point A will move towards down the hill of this inclined plane. So that is going to be my final answer to this problem. This problem is little bit difficult, but it gives you the complete insight that at times, you not only have to solve for your kinetics, also you require to solve your kinematics. So this is a unique problem. You can say, if you ask me, this is a tough question. This is a difficult problem. So you know that you have to go through the intricacies of this system and solve it like that. Okay. So if you have any query, clarification, you can ask me. Otherwise, you see that these are the two problems which I intended to share with you while explaining the basic physics of the GPM. Okay. So since we have already finished our translational motion, already finished the pure rotational motion, and today in the live class we finished the GPM. With this, we come to an end to the discussion of rigid body kinetics. So next time when we will be meeting, we will take up the new chapter, and that is what? That is called the work energy equation in case of rigid body. So at this point of time, I stop my recording and open the discussion for your clarification and